Well, hello everyone. This is Roger Sakach, and I'm here to talk today about my oil material balance spreadsheet. So, before I get going too far, let me just chat a little bit about what material balance calculations are. So, what we do when we do a material balance analysis is we take into consideration the production and injection history of an oil reservoir, and we try to characterize whether there's any aquifers in place, whether there's an initial gas cap in place. We characterize what the PVT properties are, etc. And we take that information and we combine it with the historical pressure, reservoir pressure data, and do some analysis. And what comes out of the analysis is estimates of the original oil in place and the original gas cap size and the original solution gas in place, etc. And material balance analysis is useful, again, because it quantifies the size of these resources. And that can be very helpful when we're doing things like development plans for our reservoirs. In addition to that, it may also be used as a precursor to reservoir simulation. So let me walk you through a very simple example, and my intention is to then take that example and do the analysis and show you how my spreadsheet works. Here is the example that I wanted to present to you. So this is just a very simple case of a oil reservoir that's initially undersaturated. It does have some water injection that takes place, but later on in the life. And eventually there is water production that occurs too. But prior to that, the field is producing 2,000 barrels a day of oil, and then due to the pressure declines in the reservoir from depletion, then the production will decline. Now, what also happens in this particular reservoir, we're initially well above the bubble point. We're highly undersaturated. So there's a significant period of time when we're simply producing at the solution gas oil ratio. However, when that bubble point is reached, then we'll see some higher GORs. And the reason why eventually, in this case, the GORs fall back down again is due to the water injection that takes place, which drives the pressures up. Okay, so that's a summary of the historical production and injection data for this particular field that we're going to analyze. What we also have is we have periodically the operator will go out and obtain pressure surveys from the reservoir through buildup analysis and record those reservoir pressures. And you can see them down here in this graph. You can see that the initial reservoir pressure is 6,000 psi, and as time goes on, the pressures will decline, and the bubble point pressure in this case is around 2,200 psi. So we'll hit the bubble point around this point here. And then around this time where my cursor is, water injection takes place, which causes those reservoir pressures to rise again. Okay, so we're going to now analyze that data. And here is the material balance spreadsheet that I've been mentioning. Now there's a number of tabs in here. The first few tabs are related to PVT properties, so let me walk you through that. So these PVT correlations are the same correlations that were originally in place for the HP41 calculator using the petroleum pack that was quite popular in its day. So I've incorporated those same functions into the Excel spreadsheet, and so consequently I'm able to then go in and just sort of change any of these numbers in green. For example, I could change the solution GOR up to 500 standard cubic feet per barrel, in which case what it does is it changes my bubble point, and it changes, now you're seeing a solution GOR over here of 500 standard cubic feet per barrel. So relatively easy, we can come up with different correlations. I'm going to put that back down to 300 cubic feet per barrel for a solution GOR, and we've got temperatures, we've got gas gravities, API gravities of the oil, so on and so forth. So what we can see is that the calculated bubble point pressure is 2286 psi, which is right at that point there. This is why the solution GOR drops from 300 standard cubic feet per barrel above that pressure, and below that pressure it drops off. On the other hand, actually, let me get rid of the viscosity data here. I'll just hide that for a second because it's really not necessary to be doing material balance calculations. We really don't need the oil viscosity data. So, and then I'll just, why don't I just rearrange the scaling on the y-axis here. Let me put a number in here. That way we can see things a little bit better. So as far as the formation volume factor goes, you can see at the initial pressure it's at about 1.17, and it rises slightly until we get to the bubble point. It's up to about 1.19 at that point, and then after below the bubble point it drops off fairly rapidly. Okay, so we're going to use those correlations. We're going to use these numbers that come out of the correlations in our analysis. Now, this tab here, the gas properties tab, will give us what the gas PVT parameters are. It's going to use the same temperature and the same gas gravity that we'd input in the previous screen. In addition to that, we can also enter H2S and CO2 properties, etc., or percentages, and it'll recalculate our Z factor in blue and our gas expansion factor 1 over Bg in green on this axis here. Okay, so again, those will also go into the material balance calculation. And then finally, we've got the water properties. We do have the ability to change the salinity of the water, which is going to impact slightly the compressibility of the water and the viscosity of water, both of which are necessary to determine water influx volumes using aquifer models. Okay, so we're going to use all of those correlations. Now there is an option here in the spreadsheet if you have your own, if you've got your own laboratory analysis, or if you've got your own PVT correlations that you feel more comfortable using, you would enter that data here on this spreadsheet here. So there's a column for the pressures, for the oil formation volume factors, the oil solution GORs, etc. And you can go with that instead. Okay. And then so let me now jump to the material balance side of things, and I'll just sort of remind you a little bit about, or tell you a little bit about how the material balance calculations work in this spreadsheet. So really I have two tabs. I've got one called material balance, which is more of a conventional material balance analysis. It does its analysis using the straight line method that sort of was pioneered, if you will, by Havelina and O'Day back in the, was it the 40s or 50s. They've written a couple papers on the straight line analysis, and that's really what this is based on. And then also there's another tab here which we'll get to eventually. It's called the history matching, and it's going to allow a more fine-tuned bit of information that's going to come out of it. It's going to allow detailed pressure calculations as a function of the historical production rates that we have for the field. It's going to calculate drive indices over time, and it will have the ability to show you fluid saturations over time as the fluid saturations change within the reservoir. And it also will do the voidage calculations. It'll tell you what the voidage replacement ratio is if we have a reservoir that either has water or gas injection or aquifer influx. It'll take those numbers and convert them into voidage replacement calculations. Okay, so let's stick with the material balance tab at this time. Now, there's a number of bits of information in the green, as you can see, that need to be entered before we can actually do our analysis. So I'd shown you earlier the production plots, production and injection plots, and what I've done is I've taken the cumulative volumes over time. Here's the time array, and I've taken the cumulative volumes and entered that in there, and also the pressure data, where pressure data was available. I've entered that here in this tab. And we've also got cumulative gas production volumes. There is no gas injection for this particular field, so they're zeroed out. Cumulative water production volumes, as you may recall, we start producing water towards the end of the life for this particular field. Prior to that, it was 0. And we also have some injection volumes, water injection volumes that are in there. They're captured within that, within those columns. Now, for this particular field, I'd mentioned that there is no aquifer. Okay, so we're going to put a 2 in here because that's what the question is. It's asking if you want to consider water influx. And in this case, because we have no aquifer, there's no need to consider water influx, so I've got a 2 there. Now this one down here, this is the M value, which is the ratio of the initial free gas volume at reservoir conditions. In other words, the gas cap size divided by the initial oil volume at reservoir conditions. Here we're highly undersaturated, so that M value has to be 0. The water saturation, initial connate water saturation for this particular reservoir, we're going to say is 30%, and let's say it has a porosity of 15%. Okay. Now down here, we do have the ability to use a correlation for the rock compressibility, which is here. I've used a correlation that's provided in the Craft and Hawkins document or book to calculate the rock compressibility. We do, on the other hand, have the ability to, if I were to put a Y there standing for yes, I can put in any rock compressibility I wish. And it will override the rock compressibility down here. The water compressibility comes directly from the correlations that we talked about earlier. Okay. Now the aquifer properties, again, in this particular case, we don't have an aquifer, but if we did, we would have to identify whether we're talking about an edge water drive, which is modeled in this spreadsheet from the Van Everdingen and Hurst calculation. It also has the ability to model a bottom water drive and a linear drive. Okay, so we can put it in the radius of the oil leg. We can put in the thickness of the aquifer, the permeability of the aquifer. It will take in the viscosity of the water from the correlation. And you can enter in the dimensionless radius here, which is representative of the size, the relative size of the aquifer as compared to the oil leg. And then there's some other information here. If you're looking at a bottom water drive, you can fill this information in, or a linear drive. You can decide whether you're looking at a finite or infinite acting linear drive reservoir and put in the dimensions, the width and the length of it if you wish. But again, in this case, we don't have an aquifer, so we're simply going to put a 2 there, and it will the spreadsheet will therefore ignore all this information over there. Okay, so at this time we have everything in here, and so let's sort of take a quick look through this spreadsheet and let's see some of the results. So the first thing that we have over here is it's telling us what the cumulative gas oil ratio is, and the solution GOR, the water compressibilities, the formation oil volume factors, etc. They're all tabulated in here from those correlations which we've picked. It will show you the drive indices, but we'll get to that here in a little bit. And it also calculates a variety of what I'm referring to as straight line groups, which are plotted together in certain scenarios to allow us to determine what the oil in place is, etc. Okay, so let's move on over to the right here, and we're going to get to the meat of the analysis. So, but before we go on, let me take just a few minutes to reintroduce you to what the material balance equation is. And I wanted to just sort of explain to you what that straight line approach is, because it's necessary in order to understand which graphing technique we're going to make use of. So here is the general form of the material balance equation, and it's solved on the left-hand side for N, which is the original oil in place. And it's a function of obviously the cumulative oil that's being produced and the PVT properties, which are functions of pressure themselves. This WE is the cumulative water influx. There's your M value there, which is the size of your, which is the relative size of your gas cap, water injection, gas injection volumes, etc. So that's the general form of the material balance equation. Below it is the same equation, but it's been formulated. It's been moved around a little bit, and we've taken the individual parameters and we've sort of grouped them. For example, F is equal to this grouping of parameters. EO is equal to this grouping of parameters. EG, so on and so forth, and EFW. And so because now we've grouped the parameters, this allows us to rewrite the material balance equation in a different way. It's in a simpler format, but still the same equation. Now, as you recall, the specific problem that we're working with here is the case of a initially undersaturated reservoir, i.e. there is no gas cap and there is no water drive. Fairly simple case. So in that case, we're going to take that material balance equation we were just looking at, and we're going to realize, first of all, M is 0. There's no gas cap, so we're going to strike that out. And we're also able to strike out the cumulative water influx. How can there be water influx if there's no aquifer? So both those come to 0. And so therefore the equation can be rewritten in even a more simplified form, right where my cursor is here. Now, if we take that equation and we solve it in a linear form, so what we're going to do is we're going to put some of the parameters on the left-hand side of the equation, and we're going to plot those on the y, or vertical part of our graph. The right-hand side of the equation will contain a couple of terms which we're going to plot on the x-axis of the graph. And when you look at that equation and you look at it as a straight line, you will quickly realize that with this graphing technique, n must be the slope of that line. And we also realize that the intercept is 0. Okay, so that's really what we're going to be doing. We're going to graph this group of terms versus this group of terms. We're going to draw a straight line through it. Hopefully our data comes in a straight line, and the slope of that data will be the original oil in place. And we're going to make sure that that line goes through the origin, because there is no intercept in this equation that you can see. So the intercept must be 0. Okay, so where is the data? The data is just above it here. Okay, so let me zoom out a little bit so you can see it. And it actually looks pretty good. It looks like a nice straight line. Okay, and so if I take this line and it's sort of pinned at the origin, and I sort of drag it up, and if I were to put that down there, you can see that it makes a very nice straight line. The thing that's interesting about this is you can see the timing of these points. Our first measured point is right down here. Our second measured point then moves up to the right a little bit. Our third measured point here, our fourth and our fifth measured point over here. But as we start injecting into the reservoir, we start trending back the other way. There's 6, there's 7, 8, and 9. So it's interesting to note that these points sort of move around. Having said that, they are all lying on that same line. Now, what are we going to do with this? Well, we're going to calculate the slope because the slope is equal to the original oil in place. So let me just move this line out of the way here for a second. And if we come up here and just sort of overlay our cursor here, we see that that point is the x is 0.07045 and the y coordinate is 7.078 million. Okay, so the slope is the change in the y divided by the change in the x. So in this box down here, there's a place where we can type in the change in the y. Well, the change in the y is simply this number, this y coordinate here, because we're going through the origin 0, 0. So I'm just going to type in 7078476, 7078476, and over here in the x it's 0.07045, 0.07045. Okay, so those inputs allow us to calculate the slope, and the slope is our best estimate of the original oil in place. Let me put this line back up here so anybody looking at it later can know what we're doing. Okay. So that's what we've done. We've used that line to identify that this pool seems to have about 100 million barrels original oil in place. Useful information. What are we going to do with it? Well, I mean, we could stop there and we could start identifying what we're going to do with 100 million barrel oil in place pool. Is that a big number? Is that a small number? How are we going to develop this pool? But before we go there, let's do some history matching. And now that we know that we're dealing with something about 100 million barrels, we're going to go to this history match tab and we're going to type in 100 here. Okay, and we're going to put in a similar fashion, we're going to fill in some of these other green boxes. So again, we're not dealing with an aquifer. We're going to put a 2 there. Our gas cap size is 0. Initial water saturation was 30%. Our average porosity is 15%. Okay. And again, we have the ability to put in a variety of numbers here which can characterize the aquifer, but we don't have an aquifer in this case. So the 2 is going to just simply tell the spreadsheet to ignore all those inputs. Now, what we are going to do here is basically I've already got this thing set up. So again, I've got all the cumulative volumes over time put into the spreadsheet. Here's time going down. Here's your dates. And here's all your cumulative production and injection volumes in these green values over here. But what we haven't got in here yet is our pressures. So the trick is to determine what those pressures are. Well, we've already told the spreadsheet, this history matching spreadsheet, that our oil in place is 100 million barrels. And the spreadsheet is able to say, okay, well, you're telling me you've got 100 million barrels. At this time, your cumulative volumes produced and injection volumes are these numbers here. Therefore, through material balance, it should be able to calculate what that pressure is. So the way my spreadsheet handles this is it does it iteratively. So we've already told it here that the initial pressure is 6,000 psi, which is true. We're going to sort of start the spreadsheet off by typing in. I always go with something that's close to but slightly less than your initial reservoir pressure, and just sort of carry that down as a first pass. Okay, so that's going to be copied down. We've got 5,900 psi all the way down, and you can see that we're not really even close to being correct at this time because we're getting significant errors. And simply by, if I hover over this point here, what it says is that these correct values of pressure must be determined by trial and error. And in order to determine them, we can simply press Control S. And when we hit Control S, it will automatically, the spreadsheet will automatically go row by row, and it will iterate, and it will identify what the true pressure is until that calculated error becomes zero. And then this is what we can feel comfortable with going forward. Before we hit Control S, however, there's a couple of things I have to mention to you in order to set your spreadsheet up properly. First of all, we have to use an add-in. We have to use this solver add-in, which comes with Excel. Normally, it's sort of sitting down in this region here, and we just simply have to highlight over top of it, hit go, and then it moves it up into the active application portion. So that's already been done. It's sitting there, but you'll need to do that also. Now, the second thing we need to do is activate it. So the way we do that is if you come into Visual Basic, the way you go into Visual Basic is you hit Control F11, and that will bring up the Visual Basic component. Now this macro that you're looking at here is the macro that we need to run in order to iteratively determine those pressures. However, in order to have it work, we need to go to Tools, References, and we have to make sure that this box that next to Solver is clicked on, and it is, so we're fine. I can X out of this, and once you have those things set up, you can go ahead and hit Control S, and it'll take 4 or 5 minutes, and it'll run through, and it will change all these numbers, and the calculated error will be zero. Now, from time to time, maybe if you're injecting a certain amount of volume or the aquifer is a certain size, it will get hung up. And so you have to use a little bit of creativity from time to time in order to get these things to get you to a correct answer. But generally speaking, it works quite well. So what I'm going to do at this time is I'm going to just sort of run these numbers, and it's going to take 4 or 5 minutes. So I will talk to you in a couple of minutes after I've rerun them, and then I'll show you the results. Okay, we're back. So that took about 4 or 5 minutes, and the spreadsheet went through and it calculated. Basically, it refined my original estimate, and it replaced it with some new pressures. And now you can see that the calculated errors are all zero. So let's see if this makes sense. Let's take a look at the results. So if we just sort of scroll to the right here, let me move down a little bit. Just sort of scroll to the right. Again, here's your PVT properties, which is coming straight from those correlations that we were talking about earlier. It's now calculating on a point-by-point basis what the original oil in place was, and you can see that these numbers are now very, very close to 100 million barrels that we saw from the linear material balance calculation, the straight line technique that we had performed on the previous tab. It also tells us what the initial gas cap size is. Well, the initial gas cap size, it's saying in each case, was 0, which is correct. We're well above the bubble point. It calculates the depletion, or the various drive indices, all of which totals up to be 100%. So you can see that these things total up to be 100% for each of these rows, and we'll graph that up and show that to you in a second. This box up top is a nice little summary I've put together. First of all, it says the initial reservoir pressure is 3,700 psi above the bubble point, and it shows that there is no initial gas cap in place. The initial pore volume, it's able to determine what that initial pore volume was, and it also has calculated for us what the initial hydrocarbon pore volume is. In other words, what portion of the pore volume is actually filled with hydrocarbons, whether it be oil or free gas. It tells us what the original oil in place is, and it also quantifies for us what the original gas in place is. From two perspectives, it tells us what the original free gas is. Well, in this case, there is no gas cap, so it's clearly zero, but we do have 30 BCF of original solution gas in place for a total of 30 BCF of total gas. And it also tells us what our initial connate water in place is. In this case, about 50 million reservoir barrels of water. Okay, so to continue on, there's a variety of things that it's able to calculate here. Let's see, it's telling you then what the oil recovery factors are. It's telling you also what the current M value is. So again, initially we're undersaturated, so M is 0. But as we hit the bubble point, we start getting a little bit of free gas. So there's actually a secondary gas cap that forms. And then when we start re-injecting, then that gas goes back into solution and the gas cap goes away. Okay. It also tells us what the reservoir pore volume is. Now, the pore volume is a function of the rock compressibility, so that pore volume actually is not a constant. It changes as the reservoir pressure changes. So you can see that the pore volume, the reservoir pore volume is, it changes ever so slightly. Here is a summary of the fluid saturations over time. 70% oil initially, 0% free gas, 30% water. However, as those pressures drop, the various saturations change. It tells us what the water influx volumes are as a percentage of the pore volume. Now, in this case, there is no aquifer, so they're obviously 0 straight through. And this is just a summary of the production rates and water cuts and GORs, that the historical numbers. Okay, so where it gets more interesting is when we come over here and we start looking at some of the graphs that come out of the spreadsheet. Okay, so there's a summary of the graphs. And again, here is just a repeat of the production data that we had entered into it, with the GORs, the oil rates, the water injection rates, and the water production rates over time. This is the same data, but it's relative to cumulative oil production. Okay, now down here, let's zoom into this a little bit. These graphs here show reservoir pressure over versus time. And so initially, again, our reservoir pressure was initially 6,000 psi. And as we produced the reservoir, the pressures dropped, hit the bubble point pressure, which is again around 2,200 psi. So we're slightly below the bubble point pressure. And then we started injecting and the pressures rose. Well, when we begin injecting, the program is able to calculate the voidage replacement ratios, the instantaneous voidage replacement ratios, and you can see at times these were well above 1, indicating that the pressure would be rising. And later on, when we start producing some water, those voidage replacement ratios drop, but are still well above 1, so the pressure continues to rise. Now the red points, this is where it gets interesting, the red points that you see here and here and here are summaries of our actual measured historical pressures that we had input into the previous material balance analysis. So you can see that they overlay very well with our history matched pressure information, indicating that this seems to be a valid analysis. Here is the identical graph, but it's shown relative to cumulative oil volumes. And one of the things that comes out of this is that if you have a reservoir that's above the bubble point, that pressure, and we're not injecting or anything, we're just simply producing, the pressure versus cumulative production is pretty much a straight line. You can see that. And then as soon as we hit the bubble point, it starts curving over because the drive indices are changing within the reservoir. The solution gas then allows the pressures to be maintained a little bit more than if it were well above the bubble point. So that all seems to be consistent with the theory. This is a summary over here of the fluid saturations over time. Move that back up. Of the fluid saturations over time. So you can see at initial conditions, we had 30% of the pore space was filled with water, and the remaining 70% was filled with gas. However, as production occurred, and we hit that bubble point, a little bit of free gas built up in the reservoir, a secondary gas cap formed, and then at about this time, here, we started injecting water, which is why our water saturation is now rising. And as we're injecting, the reservoir pressure rose, as indicated on this graph here, and that allowed that a little bit of free gas, to go back into solution. So at the later stages, we were well above the bubble point again, and no free gas. And then finally, a fairly complicated graph can be built here, which is a summary of the drive indices. Now, initially, the primary drive indice was the expansion drive index, which is due to the fact that we're well above the bubble point. It's mainly an expansion drive that is driving the oil towards the producing wells. But as time goes on, that expansion drive index, and as time goes on, as we begin approaching the bubble point, that expansion drive index drops, and the depletion drive index begins to rise. So they're sort of, as one's dropping, one's taking its place. And then eventually we start injecting water, and our calculated water injection index begins to rise quite dramatically. And it's replacing the depletion drive index is dropping off correspondingly fairly quickly. So at the end of the time, we're really, the main driver in this pool is that the water injection drive index that's really driving the oil towards the wellbore. One thing that you'll note is this green line here, the water drive index, is negative. It's actually below zero. The reason why it's below zero is because the water drive index includes into it the water produced volumes. So at this time, we're actually producing water, which actually indicates a negative index for the water drive index. So that explains why that thing is slightly negative at that point. And I think really that's it. I hope you're happy with the spreadsheet to the point that you may be interested in downloading a copy. By all means, go ahead and do that. Tell your friends. I do believe this is a helpful tool that should make your future engineering that much easier to handle. Thank you.